Okay, so if you're watching the video, the first thing you want to do is read the first 3 pages of chapter 14. So up to the about middle way through page 328 from page 326, which looks like this. You have this example of the stoplight. So our next unit is going to be on probability and all kinds of different basic probability questions. The AP exam never asks you for very hard probability questions. It just asks you about some of the basics. This is going to be one of the most mathematical parts of the class. And then we're going to attach probability to designing experiments, observational studies, doing sampling, and look at z-scores and bring everything together as we get into our last tiny bit of this semester. We're mainly going to use probability, mainly going to be doing probability for the rest of the semester though. And then we're going to bring it all together at the end of this semester going into next semester. So this is probably the most mathematical, like I said. So you guys looked at this little example where they talked about the idea of coming to a certain stoplight every day on your way to work or on your way to school, right? And of course stoplights have some kind of set pattern in them. Some stoplights have a sensor, but unless there's a sensor, there's some kind of pattern that they're following. So is that stoplight phenomena truly random, guys? Well, of course not. But is the event of you arriving at a stoplight random? The answer is yes. No matter what, it's going to be random because you're not a Terminator. When you get out of bed, you're going to do so even if it's slightly different each day, even if you always set your alarm for the same time. It's going to be slightly different each day when you get up. It's going to be slightly different when you leave your house. It's going to be slightly different how you step on the accelerator and how you interact with traffic on the way to that stoplight, and all those things in combination are going to lead to that being a random event when you arrive at the stoplight, even if you're like a super crazy OCD person, if you guys get my meaning there. So that's definitely a random event. So how could you, despite that being a random event, figure out how often the stoplight is actually turning red? Or how often you hit it when it's red? So that's where this little chart comes in handy. What kind of diagram is this again? It's got percentages here. It's got x's here. This is some kind of relative frequency diagram. Okay? So you can see that it looks like the first time this person hit a red light, because after the first instance, the first outcome, the first trial, we might say, I think that's a better way we've been using the vocabulary. After the first trial, it was a red light, so it was red 100% of the time. Then it dropped on the second trial to 50%. So what happened on that second? It was green. Then on the third one, it went up to about 67%, looks like. So the third one was red. You can kind of see how this develops over time. But what's key here is not the individual outcomes, but the long-term trend in what's happening. So what's happening over the long term is, can you guys see it kind of settling down, the percent of times that the light was red? And you should clearly be able to see that settling down to about this number right here, which is about 35%. So whoever programmed this light must have programmed it to be red about 35% of its time being on. Does that make sense to you guys? So the whole main important part here is that random phenomena, we're going to focus on the long-term relative frequency of an event. And we've seen that definition before, but it is the holy grail of what we're talking about in this class. Long-term relative frequencies. So I wanted to define some basic vocabulary. You guys read about that vocabulary on page 327 and 328. So what are some of the key terms that we need to know here? So I wanted to put those down. So let's see. I'm just going to delete this first thing here, give myself some more space. So key, let's see, the basics of probability vocabulary. These are all things you should be very comfortable with. So I'm going to define probability. What does probability mean technically? Probability is what I just said. It's an event's long-run relative frequency. That might be a little bit too wordy for you, so you should always be paraphrasing things in your mind, trying to think about them other ways. If you want to be good at this kind of thing, that's what is the key. So an event's long-run relative frequency, this is basically the percentage of the time it happens in the long run. If you really go out to infinity, you find the actual true probability. And that's what we're going to be doing in this unit, is calculating the easier probabilities the real way instead of with a simulation or a study. We're going to be doing the math the real way, because when you can, that's of course the best way to do it. Sometimes it's really hard though, or just really long and time-consuming or expensive, so that's not the way we do it in all cases. So most of the rest of this year we won't be doing it the real long way. So we need to define what an outcome is. I think we've already kind of done this in simulations. That's whatever happens during an individual trial or an individual run. An event, I think we've also defined before, but I'm going to define it again in terms of probability. An event is any combination of outcomes. And the last thing that we're going to need is kind of new, but kind of not new at the same time. We didn't really do it very rigorously before, but we're going to start to get very specific about what the word independent means. Independent for us is going to mean when the outcome of one trial doesn't influence or affect the outcome/chance of another trial. That should make sense. I mean, the word is pretty intuitive, but using it mathematically might be a little less intuitive than what you're used to. We'll see. I mean, it depends who you are and everything. So there's some of the basic vocabulary of probability. The other term I want to get in here, which we're going to read about here in a second, is the law of large numbers. This should be something you probably haven't run into in the past. So the law of large numbers, I'm going to have you guys read about it a little bit, but I'm going to define it first. It's the long-run relative frequency. I just used that in the definition of probability. So, in other words, I could just say the probability. So if you want to just delete this part, you can. So it's the probability of repeated independent, guess I should put a comma, events. And the law of large numbers, being a law, it makes a claim. It says the probability of such events settles down to the true probability as the number of trials, help me finish, increases. Exactly. In calculus, we might write this like this. We'd say as n approaches infinity. So, of course, the law of large numbers has a proof. That proof uses high-level calculus beyond what any of us have done yet, even if we're in Calc 2 right now. So this has a proof. It was discovered by one of the Bernoullis. I think it was Johann Bernoulli, but you guys are going to see if I'm right about that, because you're now going to read page 328, at least the top couple paragraphs. Then I'm going to read the bottom two and emphasize some things for you. So I'll give you a second to do that. So if you're watching the video, you might want to pause it now and read the rest of page 328. So I'll see you in a second. Okay, so you should have had enough time now to look at the rest of page 328. So I want to talk a little bit more about the law of large numbers. This is basically just the mathematics that proves that what you expect to happen does happen. I think probability in this case is pretty intuitive. I love Jacob Bernoulli's quote that says, "For even the most stupid of men is convinced that the more observations have been made, the less danger there is of wandering from one's goal." He's actually the first guy who proved this mathematical concept so that then we could rely on it to do all kinds of other different things involving high levels of science and, just high levels of statistics like this. So the laws pretty much misunderstood by a lot of people, though. So this is actually a really dangerous thing if you understand it the wrong way, especially if you like to gamble. So I'm going to just read a couple more things out of the book. It says, "Yet the law is often misunderstood because the idea of long run is hard to grasp. Many gamblers, for example, believe that a number that has not come up on a roulette wheel or in the lottery for a long time is due to happen because that's the way reality is. It's fair in that way, right? But no, it doesn't work like that at all. So they give the law of large numbers as their reason. In fact, usually they call it the law of averages or some similar term. But they really are talking about a distorted, skewed version of this idea, which is true. The law of large numbers doesn't apply to short-run behavior. The problem is that probabilities even out only in how long? A long time. And if you actually approach infinity, that takes how long? A long time. So if you think that roulette, for instance, if black has just come up 6 times in a row, like, because the casinos take advantage of this. They show, there's this big fancy thing at the casino that shows like what numbers have come up and what colors they were and all this stuff to try to entice people to bet. Because if there were just like 7 blacks in a row, some people are going to think, oh, well, black is popular today, so I'll bet black. Or, man, red hasn't come up for a while. Because 7 blacks have come up in a row, that must mean red is due to come up next, right? So there must be a greater chance of red coming up. But if those are truly independent events and someone's not like fudging how they spin the ball on the roulette wheel, that's completely erroneous reasoning. Each event is truly independent from one another if they're spinning it the right way. It's a random event. So you can't expect in the short run, like the next roll, to do anything in particular. That's the law of averages, and that's false thinking, and casinos especially encourage you to think like that if you ever go and gamble. So it's very dangerous thinking to think like that. So off to the side it says, don't let yourself think there's a law of averages that promises short-term compensation for recent deviation from what you expected. You don't expect a whole bunch of blacks to come up in a row, but it's possible. And in fact, it happens quite often, more often than you might think. A belief in such a law can lead to money lost in gambling, but also to poor business decisions. This kind of thinking is just completely erroneous and bad, and it's so easy to get trapped in that net. So, just because something hasn't come up for a while, if it's a random phenomena, so what? Okay? In fact, the so-called law of averages doesn't exist. The common misunderstanding of this law is that random phenomena are supposed to compensate for what happened in the past. So if recent results have fallen to one side of what is expected, somehow results on the other side are due because everything must average out in the end. That's not true. Is a .3 hitter in baseball who has struck out the last 6 times due for a hit his next time up? No, if you know anything about baseball, it's totally not the way things work. Come on. If you've just flipped a fair coin 5 heads in a row, is the next flip more likely to be tails just because it owes you a tail? Is the coin feeling bad? It's like, man, I gotta make this even out. I don't think that's the way things work. I'm not thinking that's the way it works. So that's the idea. No, random phenomena don't work this way. The coin can't remember what happened. It's not going to make things come out right. I'm using air quotes there. In fact, if you flipped a fair coin several thousand times, you'd find lots of long streaks of heads. And if you looked at all streaks of 5 heads, we'd see that on average the next flip is just as likely to be tails or heads even after a streak. So if the law of large numbers promises that given a very large number of trials, a very large one, the distribution of subsequent results will eventually overwhelm any recent drift of streakiness, but it takes a long time. And people don't really understand that concept of long time unless they've had a class in calculus, usually. And some people who've had a class in calculus still don't really understand it. But that's one of the main points in calculus, is to learn about what long time stuff really means. Okay? So that's key to understanding probability. There's another great example on 329. It says, the law of averages in everyday life. Here's something all kinds of people do. Some of your parents might have done it. Dear Abby, my husband and I just had our 8th child. Another girl. And I am one really disappointed woman. I suppose I should thank God she was healthy, but Abby, this one was supposed to have been a boy. Even the doctor told me that the law of averages was in our favor, 100 to 1. Silly doctor. Nature doesn't care. Births are random. it doesn't care what happened in the past. It's still 50-50 likely. Each child's independent of another one unless, like, some kind of medical complication might occur that might change the independence. But that's the idea that we're working with here. So if you guys want to see a little bit more formal stuff on the math, you can look at pages 332 through 333 on your own. I'm going to kind of summarize what they have in them right now. It's some pretty basic stuff, honestly. This first chapter is really basic probability stuff. I think it's stuff you should know from another class or from middle school or something like that. So let's go and look at some really basic probability laws for actually doing the math, and then we're going to do some examples on that chapter 14 handout that I gave you. Okay? So what are some basic ideas to do the math? Well, here's one. For any event, let's call it event A, the probability has to be between 0 and what other number? 0 and 1. The probability of A, which you'd write like this, has to be between 0 and 1, because 1 represents 100% and 0 represents 0%. You can't have a probability anywhere but between 0 and 1. That's an important idea. The probability an event does not occur, we have some special notations for it. The most common one you're going to see is this, is notated. The probability of A, sometimes they go A sub C, let me get this in. The probability of A like that. Sometimes that's called the complement, or the probability that an event does not occur. Let me put this in here. So it's called the complement and is notated this, or more commonly I've seen it like this. The probability of A, hold on a second. Oh, where'd it go? Silly word. Or it's got a little bar on top, just like the average thing. This is also this is a more common way to say A complement, is if you put a little bar on top. Now, how do you do the probability of A complement? So we compute A complement's probability by doing 1 minus the probability of A. That's it. I think that's something you should have already known as well. Then, two last things. The probability of A or B, when we have two different events, and we want to think about what is the probability of one or the other, we're going to be working with that's going to come out to the probability of A plus probability of B. Given, I don't have time, those events are disjoint. So what's disjoint? I'm going to show you in a second. So it's very simple. If the events are not disjoint, you have to do it a little bit differently. We're going to look more at that tomorrow and on Monday. So I also want to do the probability of A and B. You guys know the symbols for A or B and A and B, right? What does OR look like as a symbol? It's the U shape, right? Union. And is the upside down shape, right? So I'm just not writing them like that because I don't want to make this harder. So the probability of A and B happening is just going to be the probability of A times the probability of B. But that's also only true in certain circumstances. Today we're just working with easy circumstances, and I'm going to look at some Venn diagrams with you in a second. That's given that those events are independent. Okay? So let's look at just a couple things, and then we're going to start looking at those problems in the book. So if you look at page like 332, they're going to have some nice diagrams and go over this a little bit more in depth. So you can see a great example of what the complement looks like here. If the blue circle is all the chances of getting Some event A, what's its complement? Everything outside. And how much area is in this box, this universe? 100%, 1. Yeah? Here are two disjoint events. Two disjoint events are two events that are completely separate. They have no overlap, no intersection. So events have to be disjoint for you to be able to do the OR thing by just adding. If they overlapped, you've got to be a little bit more careful. And we'll start looking at that tomorrow and Monday. Here's an example of two other events, A and B. Are these events disjoint, guys? Clearly not. They clearly have some overlap. But two events like this can still be independent. And you can see where on the picture is their intersection. That's just in the middle, that little grayish part. That's the probability of A and B. You can get that by just multiplying the probabilities together. But that's, again, they have to be independent. Sometimes they aren't. We'll look at situations where they are, and some where they aren't. So I thought we'd start looking at some examples on Chapter 14, Quiz A. So let's go and do this one. So most of these are simple little quick computations. It's going to be the rest of the hour before I can get you, Caleb. Or what? Yeah, you can get those. Yeah. You have to ask me that. Okay, so first one. These are some good questions just for you guys to know, I think, actually. Multiple choice. We've got 4 possible answers, so A through D on this history exam. What's the probability? We're assuming we just guess here. We have to assume that. So if you just guess, what's the probability of A getting none correct? I think all we need to do all these problems on here is those basic ideas that we just talked about. So what do you guys think? What's the probability of getting none correct? How could I do that? First, the key is rephrase these in a way that makes sense to you. Paraphrase. That's equal to the probability. I want to see statements just like this on yours. That's equal to the probability of them all being wrong. Do you have to write exactly that? No. You just have to write it in a way that makes sense to you. What's the probability of 1 being wrong? If you just guess. There's 4 questions. Probability of getting it wrong is 75%, right? Now, the probability of getting them all wrong is going to be an AND or an OR statement, you guys. Yeah, I know, but this is just the first question. To probably get the first question wrong is 75%. To get them all wrong, you're going to have to get the first one wrong, and then the second one, and then the third one. Is this AND or OR? AND. Do we multiply or add for AND? We multiply. So I could write 0.75 5 times in a row, but the better way to do that is say what? 0.75 raised to the 5th power. So you can put that in your calculator. I'll do that for you today. It's 0.2375. So there's a 23% chance of getting them all wrong. Does that make sense to you guys? The key here is that you realize that that's an AND statement, and AND means multiply. Okay? What about getting all of them correct? Let's rephrase that. That's equal to the probability of all right. Probability of getting 1 right is what? A quarter. And the next one right times another quarter. And the next one right. You guys get the idea, right? It's going to be 0.25 raised to the 5th. Put that in your calculator and you get 0.00098, which is equal to 0.098%. Not a great chance of that happening. What about getting at least 1 wrong? This is a really key one. You want to use the complement here. Otherwise, this is a very much harder problem. So I'm going to say, well, getting at least one wrong is the same as getting it's the same as going 100% or 1 minus the probability of all being correct. Getting at least one wrong is that, right? That's the opposite. So I'm using the complement here. It's the same as going 1 minus the probability of all correct. If you try to do it the long way, man, this is like it'll take the rest of this page to do it if you don't use the complement. But this way, it's so easy. So that's going to be 1 minus what? Did we just do all correct? So it's this, right? I think if you do that, you're going to get basically point. Let me write this spaced a little better. So getting at least one wrong, how likely is that to happen? It's going to happen. Pretty much, right? So that's using the complement. Make sure you guys take advantage of the complement. Very important. How about getting the first one exactly, getting that one incorrect, and then, oh wait, let me see. They phrased it differently, didn't they? They said getting your first incorrect answer on exactly the fourth question. What do you guys think? Is this going to be likely or unlikely? I think it's going to be unlikely. So I'm not going to rephrase that. I'm going to say the probability of, etc. is going to be equal to what? Well, this is very specific. It says your first incorrect answer on the fourth question. So what happens on the first question? You got it right. What's the chance of that? Think about it separately. You guys don't overcomplicate this. The first question, there's a 25% chance you get it, 75% chance you don't. So 25%. And then you get the second one right. I'm multiplying because of the and, right? And then the third one, we also get it right. Oh man, it doesn't like my parentheses today. And then the fourth one, we finally get wrong. Come on, thingy. You write that in your calculator, and that's the way to do it. That turns out to be 1.00117. So that's equal to 1.17% chance. It's very unlikely, in fact, John. And there you go.
So you can just ignore the fifth question on that?
Oh.
Yeah, because it's on the fourth.
Yeah, because it's not.
You get your first incorrect one on the fourth. It doesn't matter.
How many questions are we going with here?
5.
So do we have to add another 0.25?
You should be able to just ignore the fifth, wouldn't you?
Good question. Can we just ignore that last question or not?
It's saying you're getting your first incorrect on the fourth.
It really doesn't apply, right? It's kind of like, well, whatever happens after that. So if we put a 0.25 in there, then we'd have to count a bunch of different possibilities that could happen and add them all up at the end. And that's what we're going to get into as we get into tougher problems. But that's not going to happen yet. So good question. Very good question, you guys. I think we can just ignore it. You've got it, Logan. Very nice. Okay, let's look at the second one. So this time we've got peanut butter M&Ms. They tell us the percentages. They want to know what happens. So first of all, I think it's called I on yours. What's the probability it is green? So what do you guys think? Probability of green. We could use the complement here. This is just common sense, though. You don't even have to think about the complement. We've got 10% are brown, 10% are red. That's 20% so far, right? 20% yellow, 20% blue, 20% orange. How much is that? 60. 60 plus 20 is 80. So yeah, you can rephrase this as 1 minus the probability of not green. And that's going to be equal to 1 minus, we just counted up how much the not greens are. How much was it? 80%. So this is going to be 0.2 or 20%. That's pretty boring. What's the probability it is a primary color? You just got to add up red, blue, and green. Or, excuse me, red, yellow, and blue. My bad. So red was what? 0.1. Yellow was 0.2. And blue was 0.2 as well, wasn't it? That's 50%. What am I technically using? What law of probability am I technically using here? Am I using and, or, complement? What? I'm using or, exactly, because we're thinking it's a primary color. That's really what? I mean, you don't have to always write these out, but this is how you should think because we're going to get harder questions soon. That's going to be the same thing as the probability of red or green or blue, except I'm lying, it's not green. I keep thinking green is primary. And or we add. That's it. Okay, the next one they asked us for was the probability of it is not orange. Could use the complement on that one, couldn't we? And go 1 minus probability. It is orange. That's going to be 1 minus, what's the probability it is orange? 20% was orange, right? So that's just going to be 0.8. Now on some of these, do you really have to think about complements and stuff? Well, of course not. You really don't have to. The goal is for you to start thinking like that because, of course, these are just like middle school level questions in general. We're going to do much more complicated probabilities. And if you can do these with the rules, you're going to be able to do those just as easily. If you can't do these with the rules, those are going to be hard. Does that make sense to you guys? So. The fourth one. Do we have a fourth one? Oh, we had a part B, didn't we? Let's see. This time we're looking at picking 4 M&Ms in a row. So 4 different M&Ms. We're going to pick 4 times. What's the probability? They are all blue. What do you guys think? Help me. What's the probability of one being blue? 20. If they're all blue, is it and or or? It's and. And means multiply. Calculator. Done. What's the probability none are green? Well, ask yourself, what's the probability of one not being green? We got green was what up here? Didn't we say 20%? Yeah. So none are green would be the first one, there's 80% chance it's not green. And then 80% chance the next one's not green. And then 80% chance the next one's not green. It doesn't like me. Stupid Microsoft. Now, Logan just asked a fundamental question. He said, are we assuming that we're putting the M&Ms back in the bag? What do you guys think? Oh, it definitely matters. Based on how we've been doing these so far, though, are we making that assumption or not? Yes, because the probabilities have not been changing. If the probabilities were changing, these would not any longer be independent events. Can you figure it out if they're changing? Well, yeah, but that's next week. Okay? So far, we've been assuming that everything is independent, that we're putting them back in the bag. It's a fundamental question. Very nice. Okay, last question here is probability at least one is red. If you're watching the video, I'd try to do that right now on your own. Why don't you guys take a second and see if you can work that out. What's the probability that at least one is red? And then go ahead and do that last one too. So we'll do that one, and then we'll do the probability. The fourth one is the first one that is brown. Okay, so the probability at least one is red. I should change that into what? 1 minus the probability that none are red. That's the exact opposite, also known as the complement. If you try to do it another way, good luck. It's possible, but man, it takes a lot of work. So this is going to be 1 minus the probability that none are red. Well, red was how much percentage? 10? So the first one not being red would be 0.1. Multiply that 4 times and you'd get this, right? 4 M&Ms. So there you go. That's going to come out to, you guys got it? No? It's 34.39% if you do that. Okay. What's the probability the fourth one is the first one that is actually brown? So that's going to be no brown, no brown, no brown, brown. So no brown is 0.9. And then the fourth one is actually brown. So that's how that would work. I think if you do that, it's about 7%. The very last question for us today. So it says, after picking 10 M&Ms in a row, you've still not picked a red one. A friend says, you should have a better chance of getting a red one on your next pick. You haven't seen any yet. Ah, great question. That really makes a difference again, right? We're assuming you're putting them back. Let's write that down. That's a huge assumption. Assuming that we are putting the M&Ms back each time, we would tell our friend to stay away from casinos or any type of game of chance because our friend is going to lose major moolah. That's what we would tell our friend. Our friend is thoroughly ingrained, has this idea of the law of averages thoroughly ingrained, and it's not going to work out for them all in the end. Now, if we were not assuming that we're putting them back each time and we've already drawn 10 M&Ms, then yeah, there's probably a better chance of getting a red one, depending on what? How big this bag is. If this bag is approximately infinitely sized, our friend's still way wrong. If this bag is really, really large and has like 10,000 M&Ms in it, our friend is also still really, really wrong. If this bag is a family size with 100 M&Ms in it, our friend might be right. Okay? So that's it for today. Yeah.